All right, let's jump right into this essential guide for electrical workers in Queensland. Today, we're basically stepping into the role of invisible detectives. And I say detectives because in the electrical industry, the dangers we're hunting down, faulty wiring, missing earth bonds, reversed polarities, they are completely invisible to the naked eye. So this explainer is going to decode the official guidelines for testing low-voltage electrical installations and will turn all those complex regulations into a really clear, actionable roadmap.
Now, everything we're talking about today is grounded in absolute, non-negotiable compliance. This isn't just a loose collection of good ideas or, optional industry best practices. This comes straight from the official Queensland Government Guide. As an electrical worker, your actions are governed by strict protocols, and really understanding the scope of this document is the very first step in making sure every single installation you touch is fundamentally safe.
So here's the deal. Testing isn't just a nice-to-have. It is a strict legal requirement. The Electrical Safety Act 2002 leaves absolutely zero room for interpretation here. When you finish an installation, you can't just flip the switch and cross your fingers. You are legally obligated to test and examine it. Why? To prevent tragic outcomes like electrocution and fires. This is really about taking ultimate responsibility for the invisible forces we work with every single day.
Here is our roadmap for this explainer. We'll hit safety and scope, essential test equipment, the visual inspection, mandatory electrical tests, and finally, the step-by-step procedures.
Okay, part 1, safety and scope. We've got to set the stage.
There are very clear boundaries to this guide. First off, we are exclusively talking about low voltage here, so no high voltage equipment is covered in these specific guidelines. Second, everything is anchored right to the AS/NZS 3000-2018 wiring rules. But honestly, the most vital point here is that a safe system of work absolutely must be in place before you even think about starting a test. We're also dealing specifically with installations using a multiple earth neutral or MEN system. You just have to know exactly what kind of environment you're walking into before you begin.
Moving on to part 2, essential test equipment. Basically, your detective tools.
A lot of folks make a massive mistake right out of the gate by using a standard generic multimeter, and that simply won't cut it when you're trying to verify the integrity of life-saving earth bonds. Why is that? Well, standard multimeters just don't supply enough current to give you a reliable picture of how joints, welds, and bonds will actually perform under real operating conditions. You need a true low-resistance ohm meter, one that's capable of accurately displaying readings between 0.01 and 10 ohms with a high current output.
200. That right there is exactly what we mean by high current output. 200 milliamps. That is the recommended minimum test current for your low-resistance ohm meter, whether it's an analog or digital meter. Pushing at least 200 milliamps through the circuit during a test is what simulates a real-world load closely enough to reveal if a connection is truly secure or if it's just barely hanging on by a thread.
But hey, just owning the right tool isn't enough, right? You have to prove it's telling you the truth. On the ohm scale, you first need to short the leads together and check for a true 0-ohm reading. After that, you verify the meter's accuracy against known low-value resistors, specifically 0.1, 0.5, 5, and 10 ohms. And the golden rule here, you do this before and after you test the installation. Because think about it, if your meter drifts or breaks during the job, all your results are totally compromised. You are proving your tools are perfectly calibrated before you trust them with someone's life.
All right, part 3, the visual inspection. Time to look for clues.
Before any meters are even turned on, your eyes are your best tool, and a massive part of this visual inspection centers right around the switchboard. Verifying these physical connections is totally mandatory before the installation ever gets connected to the supply. You're visually confirming that the adjustable protective devices are correctly selected and set. You're double-checking the main switches and isolation devices. You have to inspect the connecting devices too, the neutral bars, earth bars, active links. Is everything labeled properly? And critically, you are verifying the multiple earth-neutral connection and all the earthing conductors. Honestly, if it doesn't pass the eye test, you do not proceed.
Part 4. Mandatory electrical tests. These are the absolute non-negotiables.
Now pay close attention to this strict chronological dependency. You cannot just do these tests in whatever order you feel like. It is a highly specific logical sequence. Step 1 is always the continuity of the earthing system. Step 2 is insulation resistance, then polarity in Step 3, followed by earth fault loop impedance, and finally testing the operation of the RCDs. This sequence matters immensely because earlier tests actually prove the system is safe enough to perform the later tests. You literally have to prove your earth continuity before you can reliably test insulation resistance. And this chronological rule, it is incredibly rigid. Let's say you fail your earth continuity test and you have to go in and alter or repair a connection to fix it. Well, that completely invalidates any insulation tests you might have already done. Fixing an earthing issue forces you to step all the way back and re-verify the insulation. You can't just patch a problem and blindly move forward. You have to ensure that your fix didn't compromise the rest of the system.
Okay, final section. Part 5. Step-by-step procedures. Let's actually verify that safety.
0.5, half an ohm. When you are testing the main earthing conductor, and I'm talking specifically about testing between the disconnected NEN link at the neutral bar and the main earthing conductor down at the earth electrode, the resistance must never, ever exceed 0.5 ohms. You isolate it, you check your ohm meter, you test across that path, and you look for that crucial reading. If it's over 0.5 ohms, your earth path has too much resistance and it simply cannot be considered safe.
Now, how you actually carry out your procedural steps completely flips depending on the state of the installation. For instance, when we test for polarity, the method is entirely dictated by the supply. If the supply is connected and live, you've got to use a high impedance voltage indicator to carefully test between the active and neutral to ensure correct polarity. But if the supply is not connected, your method changes completely. You verify isolation, and then you use your trusty low-reading ohm meter to measure resistance, usually by making a temporary connection at the switchboard. The context dictates the tool, and the tool ensures the safety.
1 ohm. This is the magic number when we move further down our timeline to carrying out the earth fault loop impedance test. When you perform this specific test, you must ensure your instrument is set to the high current trip setting, not the low current no trip setting. Using that high current setting, your final result must be less than 1 ohm. Why? Because that incredibly low impedance is exactly what ensures a protective device will rapidly disconnect the circuit during a fault. If the resistance is higher than 1 ohm, the breaker might not trip fast enough and the results could literally be catastrophic.
So, as we wrap up this explainer, I want to leave you with a question to think about. When you're out there in the field with your low-resistance ohm meter in hand, are you just ticking boxes on some government form, or are you actively proving that the invisible shields in that electrical system are intact and ready to save a life? Because remember, these strict, legally mandated tests are the absolute only thing standing between a hidden electrical fault and a tragic accident. Every visual check, every 200 milliamp test, every 0.5 ohm reading, it all matters. Stay safe, trust your calibrated equipment, and stay incredibly focused out there.